There we go. Let's share the screen. All right. Oh, this is not sharing. How this works? Oh no, what happened? Super. Do you know where to control the lights? Dark. I think these are all. Turn off the light. Turn on the lights. Does anybody know how to control the? I think those are the screens. This should be bright.
What did you change? What did you touch to?
Nothing. I just changed from the PC to the. It was like docam, and then I just changed to PC. That's it. I promise. I promise. That's the only thing I did.
Okay, you turn it back off,
Not that, like,
and then turn it up.
oh, let me try that. There's another light switch. Still see? All right, we'll go with this one. Not super bright, but might as well just get started. Couple of announcements for the lab 1 worksheet. Not everybody submitted. I don't know if everybody that is here submitted the worksheet, and the people that are not here did not submit the worksheet. But some people did not submit the worksheet. If you haven't, I'll open it up again until the end of this Friday for you to submit the worksheet, because you have to show that you did the lab. You don't have to show up on Friday at the computer room. That's not required, but you do have to submit the worksheet. And there's 2 different things. One thing is the worksheet, and the other thing is the lab report. The worksheet is associated with just watching the tutorial and then doing whatever is on the tutorial, taking some screenshots, saving that to a Word document and uploading that. And then the report is due 2 weeks after that. So for lab 1, there was a worksheet that was due last Friday, and the lab 1 report is going to be due a week from this Friday. And that day also a lab 2 worksheet is going to be due, because the worksheet is really just to show that you watch the videos and you follow the videos. So basically the worksheet replaces your attendance on the day of the lab. I should probably wear the notes. So I'll open up the worksheet again. And also for those of you who got points off, I think most of the points that were taken off were because of units. So just be careful with your units. If you have stresses, they should be in Pascal or megapascal. If you have forces, well, depends on what units you are using, but they should be consistent units. So for example, if you're working with SI units, forces in newtons, stresses in pascals, distances in meters. If you are working with millimeters, and then forces can still be in newtons, stresses in megapascals. Whatever choice of units you want, just be consistent and put units. Do not leave blank units in the worksheet or the reports, because we do take points off for that. So I'll open up again the worksheet. If you have errors in the first submission from last week, you get to resubmit. If you haven't uploaded, you get to upload it this time. Yeah, we won't do this for all the labs, but just for this one, if it wasn't clear, and I'll send an announcement. I think that's for the lab one. Homework one, I haven't posted it. It will be different from spring 2021. I'll post it on Friday. So basically, things are going to be posted sort of 2 weeks ahead of when they are due for the labs and for the homeworks. Any questions? Yes. Yes. So for not this Friday we have lecture, but next Friday, the 27th, it's lab day. You don't have to show up. TAs will be there. Tina, I think, will take the first shift from 9:30 to 11:30, and then KU will take the 11:30 to 1:30. So as I mentioned, I think maybe the first day of class, you can do it on your own, submit the worksheet. You don't have to come here if you don't have any questions. You can come on that day and watch the videos in the computer lab and then just ask questions if you have questions. It should be doable within the 2 hours allotted to the lab, but you don't have to come if you don't want to. Any other questions? Again, just remember that you do need to submit the worksheet that is due for that lab. All right, so let's continue with lecture 3 on trusses. A little bit of remembering what we were doing last class. We were defining the truss element. So for an element, we have 2 displacements, which for the notation of the element, I mean, this just for any element, we always have 2 displacements associated with 2 nodes. This is node 1 of the element. This is node 2 of the element. We have the corresponding displacement values, and then the internal forces of the element. And then what I derived last time is that the entire element can be described by the following matrix equation. I'm not gonna derive it again, but just show you that the entire element basically boils down to this equation. This is E A over LE, where E is Young's modulus, A is the cross-sectional area, and length of E is the length of the element. This we typically call scalar KE, 1 minus 1 minus 1, 1, U1E, U2E. So the truss element equation basically boils down to that expression in expanded form. If you use matrix notation, this is the force of the element equals this whole thing is called the stiffness matrix of the element times the displacement vector of the element. This is just matrix in matrix notation. So that's one of the things that we defined in the last lecture. Now, the second thing is, how do we, given this equation for a single truss, if we have an assembly of multiple trusses, how do we use this equation to get a global system of equations? And for that, we were doing an example. So I'll redo this very quickly. The first thing, this is already on the previous lecture notes, but the first thing that you need to do is to define your mesh. And you have been doing this in the lab as well. What do you need to define your mesh? You basically need a list of the nodes with their coordinates. In this case, we have, this is a 1D truss, so we only have X coordinates. And then we have a list of element connectivity, where we have the element number and then the nodes that make up that element. So in this case, these are the nodes and these are the elements. And so here you can see node 1 has coordinate if you put your x at this location. Then node 1 has coordinate, I'm gonna say that it's coordinate 2. Then node 2 has coordinate 1, and node 3 has coordinate 0. Again, remember that this naming is arbitrary. I could have named the nodes from left to right, or the first one in the middle, completely arbitrary. As long as I have the correct coordinates, and as long as I have the correct connectivity. So in this case, element 1 is the one that is made out of these two nodes. It's made out of nodes 3 and 2. And element 2 is made out of nodes 2 and 1. All right, so we have the equation for one truss element, then we have our mesh. And with these two sets of information, we can assemble a global system of equations. How is the global system, what does the global system of equations represent? It's gonna represent the fact that sum of forces at the nodes equals 0 is what gives rise to go from Truss equation and mesh info to a global system of equations. So in particular, what we end up with, I will skip the assembly part for now. I did it at the end of last lecture, and I'll revisit it in a second. But if you remember, what I was doing last time is when you do the assembly process, so this thing that I was saying here, that if you have the element mesh information and you have the truss element, putting it into the global system of equations, this is called assembly. And again, I will revisit it in a second, but when you do that, you get a global system of equations. I'll skip through this one. It basically looks like that. K is the global stiffness matrix. This is called the global stiffness matrix. Oh, it's right there. Global stiffness matrix. Times D. D has the, I'll just rewrite it here. So again, that K is just the stiffness of the second element. Rewrite it here. Times D, D is the displacement. So the displacement of node 1, the displacement of node 2, the displacement of node 3 equals the set of forces and the set of reactions. And if you remember, the first node was fixed. So we don't know we know the displacement, but we don't know the force. So we call that a reaction, whereas the two other nodes have some external force. So again, this is sort of the expanded form. And this is the matrix form. It's just more compact. The matrix expression is much more compact. Yes?
Is that a plus sign?
Which one? This one?
No, the between the F
Oh,
and the
yes.
R.
Yes, yes, yes. It's plus sign. Again, I'll revisit the assembly process in a sec. But it all comes down to, you have the Truss equation. you have the element connectivity. Given those two, we can assemble this global system of equations. And then what I want to take a moment to say is the meaning of each of these lines. So we didn't explicitly derive it like that, but the first, each of these lines, like this first line right here, I'll do it with, what is this first equation right here? So it's gonna be U1 K2 minus U2 K2 equals R1. That equation is actually sum of forces for node 1. And I'll just scroll a little bit so that you see, if you go back to this drawing, you can see that for node 1, sum of forces equals 0 means reaction 1 minus F2. But F2, if you express it with the Truss equation, it will come down to K2 U1 minus K2 U2. But it is really exactly this sum of forces equals 0. That's what the first equation means. You can probably guess what the second equation means. So the second equation, that one, oh, maybe yellow is the worst possible choice. Super clear. Sum of forces for node 2. Again, if you scroll back up, you will see that at node 2, you get the external force F2, little lowercase F2, and then minus F2 of element 1 minus F1 of element 2. But if you replace this with the Truss equation, then you will have some dependence on the displacement. So that second equation really is nothing more than sum of forces equals 0 for node 2, where this capital F have been replaced by the Truss equation to depend on displacements. And then the last one, I won't scroll back up, but you can probably believe me that this last equation is basically sum of forces for node 3. So what this assembly process is doing is, again, taking that Truss equation, taking that mesh information, and is basically setting up the equations of sum of forces equals 0 for each node. Going back to the assembly process, is there a way, an easy way to assemble the linear system? There's multiple ways, and if you go back to the book, I didn't bring the book again, they define these 3 different methods. One is called matrix scatter, the other one is called direct assembly, and the other one is called gather matrices. We won't talk about any of them except the direct assembly here. So the only one that we're gonna consider in this class, if you're interested about the other ones, I would say check the book, come to office hours, ask me, we can talk about it. But the only one that we're gonna really talk about in the class is gonna be the direct assembly method. And just to remind you of what the direct assembly method is, I'll go back to this example. And so remember, for example, for element, let's say for element 2, just to remind you what the process was. For element 2, we have our Truss equation, right? So we have the F of the element 2 equals the K of element 2 times 1 minus 1 minus 1, 1. Actually, I'll remove this F. This was the stiffness matrix of element 2. And then what we needed to do to assemble was to write the node numbers corresponding to element 2 out of the element array. So if I go back to my mesh information, element 2 is made out of nodes 2 and 1. So direct assembly just means to put those node numbers in the rows and the columns. So these are node numbers from element array. And those tell you exactly where to put these entries into the global stiffness. So this is the K of element 2, and you want to assemble into the big K. In this case, there's 3 nodes. This is always number of node by number of node, in 1D at least. So in this case, it's a 3 by 3. So this should be node 1, node 2, node 3, node 1, node 2, node 3. So really all you have to do is use this to map the nodes. Here, for example, this element, K2 times 1, should go to the entry 2, 2, right? So that means that I should put it in here. That one I should have a K, do this with black. So there should be a K2 there. Then these 2 elements should be going to the entries 1, 2, and 2, 1. So I can put them in the entries 1, 2, and 2, 1. So 1, 2, and 2, 1 are these entries. And then the last one, this entry right here, that one should go to 1, 1. So that should go here. So that is the direct assembly process. It's just you have your truss stiffness matrix, and you write down the node numbers based on the element array for that stiffness matrix. And then you also write your global stiffness matrix also with the node numbers for the rows and columns. And that's it. All you have to do is look up where to map basically every entry of that element stiffness. And you just have to do that for every element. Do for every element. And at the end of that process, you end up with this global stiffness matrix that I have here, for example. Any questions about this so far? Yes.
For the stiffness matrix, is there like a right way to convert the node numbers, or is it
Doesn't matter. As long as you put the correct node numbers from the element array in your element stiffness matrix, then that's it. I'll do one more example, and then you'll do one example, and then you can really name them however you want, and it will, yeah, it will work out. The stiffness matrix might look different, but then your node ordering will be different, and in the end, it's gonna lead to the same result. Yes. So now the other thing is, okay, let's say that you have assembled your linear system like what I have in the previous slide. How do you solve it? What are the unknowns and how do you solve it? There's different methods. Again, we're not gonna do all of them. The one that you have done in 323, at the very end of 323, you did this one. You replaced one equation of the linear system by basically 1, 0, 0, 0, 0. You did do some FE at the end of 323, right? Well, if you don't remember, what you did was the middle one right there. So you replaced one of the equations by a trivial equation. What we're gonna do in this one is actually, I will do this a little bit. just to remind you of what you did in 323, but in reality, the one that we are really going to use in the rest of the course are going to be these matrix blocks. And I'm definitely not doing anything with the penalty method. It is in the book, and we can discuss in office hours, but I'm not gonna do it in the lecture. So going back to my system of equations, I have the stiffness matrix. Let me just copy that from above so that I don't have to rewrite it. Okay, so this is my system of equations. And let's say that we want to solve this. All right, so we want to solve this. And the thing to notice here is which ones are our unknowns and which ones are our knowns. And the reason why I have here this essential boundary condition is that for some of the nodes, we actually know the displacement. So in this case, we know that U1 is fixed. So we actually know the displacement for U1. So this is actually known. This you also know from now doing lab 1 that you have to specify some boundary conditions. So some node you need to say what the displacement, at least one. In this case, U1 we know. For that node, actually what we don't know is we don't know this force. So this is an unknown reaction for nodes with boundary condition. So for nodes with boundary condition, we don't know the reaction. For the other two, we actually don't know the displacement, but we know the external forces. And this is always either or. So if you know the displacement, you don't know the force. If you don't know the displacement, then you know the force. If you are not given a force, then that force is 0. But for sure, this unknown displacement known force. And again, if you don't see any force, then you still know the force is just 0. So what you can see here is that this is not a solvable system as it is, because we have one of the unknowns on the right-hand side. This R1 is kind of messing things up for us. So we need to get rid of that equation, that first equation. So the replace approach, so replace one equation. All it means is we actually know U1. So instead of solving sum of forces equals 0 for U1, I'm just gonna make a trivial equation. What is the trivial equation? The trivial equation is this, even though it's symmetric notation, if you actually expand it out, it just means U1 and then plus 0 U2 plus 0 U3. So this just ends up being just U1. And that one equal to, and we actually know the value of U1. So here, I'm gonna say U1 BC. This does not have to be 0, it's whatever the known displacement is. So this is the known displacement. In most cases, it's 0, but doesn't have to be. and then the other ones are the same. So everything else is the same. This is K1 plus K2. This is minus K1, 0 minus K1. So again, all I did was I replaced that first equation, which was, K2 U1 minus K2 U2 equals R1. I replaced it because I don't know what R1 is. And instead, my trivial equation is if you put 1, 0, 0, all I'm doing is U1, because if you expand it out, it's just U1 plus 0 times U2 plus 0 times U3, so it's just U1, equal. And then I know the value of U1, so I just write it on the right-hand side. That's it. So now there's nothing unknown on the right-hand side. So now all is known on right-hand side. Now I can actually just throw this at MATLAB and just say solve. All I need is to give it that matrix. This is a modified stiffness matrix with different, let's just call it A. And we have this new right-hand side. This is not the force of the reaction. Let's just call it B. But now you can just do, in Python or MATLAB, you can just do, well, there's no backslash in Python. We'll do it on Friday. But the equivalent in MATLAB is A backslash B. And then it will give you a vector with 3 values, which are going to be the displacements U1, U2, and U3. So this is what you have done in 323. And it works. The only bad thing about this one is that you have to go and modify your initial system of equations and basically replace the equations for which you don't know the reactions. Any questions? Yes.
So I just finished thinking last semester. I think we did something like you solve the second row to an U2 and then use that U2 value to solve the first row.
So the matrix block is going to be like that.
At least that's what we did.
Okay, I'll do the matrix block in a second. The matrix block does not replace the equation. It just splits it into 2 systems of equation. So let's write what that means. And actually, that's the one that we're going to use most of the time here. Just a little bit more systematic. So again, we have our original system of equation. Let me go back to this one. So these are original system of equations. And then again, we want to split this into 2 system of equations so that we don't have to have that R1 in the right-hand side at the beginning. So what we're gonna do is we're gonna basically split the system like this. And you're gonna see why that makes sense. Now, one thing that you need to worry about is for doing this method, you need to number nodes with BC first. At least if you do it by hand. For Abacus, it doesn't matter. This is kind of what Abacus does behind the scenes, but you can still give it an arbitrary node numbering and it will do the partitioning correctly. When we do it by hand, we actually have to name the nodes with boundary condition first, because otherwise they're gonna be, in this case, there's only one node. So it's very easy. But if there are multiple nodes, you still need to be able to make this sort of cut. And so we're gonna name these sub matrices. This is like a 1 by 1 matrix. I know it's a number. but we're gonna name this KE. We're gonna name this rectangular matrix KEF. This is gonna be KEF transpose, and it's gonna be KF. And this is why it's called matrix blocks, because this, in this case, K2 is just a number, but the other 3 are matrices. 2 of them rectangular, and the other one is a square matrix. Now our displacements are also, this is going to be some sub-vector called UE or DE, and this one is UF. And then basically all the reactions can form a sub-vector, and the external force is another sub-vector. It is the exact same system of equations that I had at the beginning. It's just represented with these matrix blocks. That's why it's called a matrix block method. And then when you do that, you can see that there's actually 2 systems of equations that we have from here. There is one system of equations, which is KE times UE plus KEF transpose times UF equals reaction. Again, this is basically like matrix vector product equals vector, but just in blocks. And the other set of equations is KEF times UE plus KF times UF equals F. So we partitioned, I use a double T into 2 systems of equations. And note that in the first system of equations, we don't know UF or R. But in the second system of equations, the only unknown is UF. So here, the only unknown is UF in the second system of equations. So that means that we can solve that second system. And this is what you were describing. So solve the second subsystem. Because if you rearrange it a little bit, this looks like KF times UF equals F minus KEF UE. And you know everything, because you know on the right-hand side, you know the forces, and then you also know the displacements of the nodes with boundary conditions. So this one is solvable, right? This you can just solve. This is just KF inverse times this. And once you solve the second subsystem, then you can go ahead and evaluate the first subsystem to get the reactions. So once you solve the second subsystem, then you can just evaluate everything here. And get the reactions. Yes.
what do all the KEs and KFs correlate to in the first place?
So KF is basically a matrix that is 2 by 2. Just do, so KF is this matrix. It's basically a 2 by 2 matrix with these values. KF and KF transpose is basically KF transpose is this 1 by 2 matrix, which just has minus K2 and 0. The other KF is just 2 by 1, which is minus K2 and 0. KE, in this case, is just a number. But if you had multiple nodes that have non-displacement, it will be a matrix. And so similarly, UE, in this case, UE is just U1. If you have multiple nodes with boundary conditions, you will have multiple nodes. UF is U2, U3, so it's a 2 by 1 vector. So it really is partitioning the matrix into other matrices. Other questions? Yes. Yeah. Question on the chat? No.
What if we didn't write down the one who knows what's boundary conditions?
Then you cannot really do this method. You would have to reshuffle to. So if you didn't name the nodes with essential boundary conditions first, then you cannot visualize it like this. You cannot just cut it like that. In MATLAB or Python, you know that you can always index your matrices with some array. So if you have, for example, some big matrix, and then you have an array with the sets of nodes that you want to, or columns that you want to take out of a matrix, you can just, in MATLAB, for example, and in Python, the same. Let's say that you have some array which has all the, so if you don't number nodes with boundary conditions first, can you still use it? Yes, but still doable, but not easy to visualize. You cannot just draw these partition lines that I'm drawing here. But you can still do it. So in MATLAB, for example, let's say you have some big matrix. Doesn't have to be this. Let's say you have some big matrix, and you only want to get out of that matrix a certain sets of rows and columns. Let's say you have an array with rows you're interested in. Let's say it's an array that has like 1, but then it skips. It doesn't go. Let's say you have 3, 4, 5, 10. I don't know, some array with rows that you care. In MATLAB, you are allowed to do, for example, a submatrix B out of A. Let's call this UE, for example. In MATLAB, you could do this, and it would get out of that matrix A, it would get out the submatrix corresponding to those rows and columns. But you can see that because, for example, in that UE array that I have 1, 3, 4, 5, 10, they are not a continuous chunk. It will do the partitioning, and actually that's, for example, how Abacus would do it. You don't have to name the nodes with boundary conditions first, and it will do something like that. It will go and get out of the big matrix, it will get the submatrix, but you won't be able to visualize a cut like I was doing. So for anything that we do by hand, by paper, we will number the nodes with essential boundary conditions first so that we can actually do this nice cut. And we don't have to worry about, oh, I need to get out these rows and these columns. So it is still doable, just not as nice. Not easy to visualize. All right, questions? Otherwise, I'll try to do a little bit of this example. So you can see for this one, there's two nodes that have essential boundary conditions. So nodes 1 and 2 have boundary conditions, and there are 3 elements. So I'll just write my mesh information. I'll speed up a little bit so that we can do. So node 1, let's say that my origin is here. So node 1 has coordinate 0, node 2 has coordinate, I don't know, but let's say 2. And node 3 has coordinates in the middle, let's just say 1. So that's my mesh information, and then my elements, node 1, node 2. Element 1 here is this one. So element 1 is made out of nodes 1 and 3. Element 2 is also made out of nodes 1 and 3. And element 3 is made out of nodes 3 and 2. So I have my mesh. Then I can do my assembly. So for the assembly, I have to loop over the elements. So we're gonna have our big stiffness matrix here. And then let's just write like I did before. So 1, 2, 3, 1, 2, 3. And then we're gonna do for every element. So element 1 is gonna be K1 times 1 minus 1 minus 1, 1. And then what I need to do is write down element 1 is made out of nodes 1 and 3. I just need to read my table. And that tells me where to put things. So you can see that this stiffness is gonna end up here, 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 and here. Again, just mapping directly from the known numbers to the global stiffness matrix. Element 2, you can see that has the same connectivity, so it's gonna look exactly the same. 1 minus 1 minus 1, 1. But it has the same connectivity, so this is 1, 3, 1, 3. So I'm gonna end up adding here element 2 minus element 2 minus element 2 plus element 2. And then element 3 that one has different connectivity. This one is 3 and 2, 3 and 2. So that one will end up here. Basically, K3. I should have make more. I need more space, but I'll make it a little bit. That looks a little bit cleaner. And then wherever I didn't put anything, just 0. And I think that's all we have time for today. Any questions? Otherwise, we'll continue this on Friday. We can solve this on Friday. Yes.
Is node or is element 2, 3 negative K3 or K2?
Oh, it's always, these are always K. Which one are you asking about? This one is minus K3 minus K3. So it's kind of small. And this one is plus K3. All right. See you on Friday.